Ready? We are live now, or still not? Not.
Let me see, because I think the link has changed already. Yes, I think we are live now.
Okie dokie. Then, so good morning, everybody. Uh, First, we want to apologize for this inconvenient um, with this small delay that we had because of some technical problems, but we are here now. And we are very happy because of our guest today um, is a colleague from Austria. She is Petra Granitza. Um, I will read a little bit about her story, about her bio. Actually, she got a diploma in physics on the preparation of porosilicon and temperature-dependent measurements of steady state and transient photoluminescence. Then she was working. She was working for Philips as a project manager. Um, she did a PhD also in physics in Graz, where she had a postdoc also on these topics. And from 2013, she's a senior scientist at the Institute for Physics at the Karl Franz University Graz. She has several papers on porous silicon and more than that on metal deposition on silicon. Actually, when I was by the time when I started doing some experiments depositing some metals on silicon, I don't know, maybe by 2010 or so, one of the references was the work from Petra Granitza. So it's a pleasure to have you here, Petra. Thank you for accepting our invitation. And yeah, you can start now. Thank you.
Okay, thank you very much for the introduction and for the invitation to this seminar talk. It's a great pleasure for me to present our work today. So we are working on nanostructured silicon and especially the deposition of magnetic materials within these structures. And we have three main routes to use the composite system for biomedical, magnetic, and optical applications. Oops. I think now the slides are not moving forward.
Yeah, they are not moving now. I don't know if you if you can stop. I don't know if you can stop sharing, Petra. Stop sharing and try to share again. Yeah, yeah, yeah. We can see your screen, so you can select the slides, maybe.
Yes, but now I cannot see my screen.
Yeah, I can see, or we can. Yeah, there is your slide.
Now, okay.
or it is not there anymore. Uh-huh. So in the bottom share screen, yeah, you are there already. Can you try to move to your slides?
I try, but they are not doing.
Yeah, they are not moving. Maybe you can stop sharing and the button below. I don't know if no. Um, oh, sorry. Mhm. Yeah, now we can see your screen where it is your name, my name, Alina's name, but
Now we can see your screen now, your presentation.
she cannot move the slides.
Yes, I cannot move the slides.
Did you use the plus button or did you use the
The
screen with
plus
an
button.
arrow?
The
Um,
screen
okay.
sharing does not work.
Okay. Hmm. Is it possible maybe if you send your presentation to Enrique, for example, and then that he can share this?
Yes.
Yeah, maybe it would be possible, but uh,
So you should have my presentation.
yeah, let me check, Petra. Yeah, it is still not here. I'm refreshing. And Petra, if you stop sharing your screen, did you stop sharing already?
Yes, I do not share anymore.
Okay, but you could not. Okay, and here, yeah, I still don't have your. I still don't have your slides. Maybe in a second or two. We'll wait a bit. Yeah, I still don't have your presentation. I it is taking much time. Now I have it.
Okay.
So I will try to share. I will share all the screen, and I think you see it, no? You see my screen,
Yes, we can see it.
and here is the presentation. Yeah,
Mm-hmm.
Okay.
Yeah.
and just to have it as a presentation here in
There.
this here.
Yeah. Yes.
Okay.
Okay, let me just mute me, and then ready.
You may continue, Dr. Petra. Thank you, and I'm so sorry for this inconvenience.
I'm very sorry, but I cannot move. Oh, yes, now I can. It's very slow, but it works. So I'm very sorry for the technical problems. So this is the outline of my talk. First, I will show you the silicon nanostructures matrices we are using. It's on the one hand borosilicon, different types of borosilicon and silicon nanotubes. And then I divided the talk into three sections. First, biomedical applications. Uh, in this case, we infiltrate iron 3 or 4 nanoparticles into borosilicon or silicon nanotubes. And I show you the fabrication of the composite, followed by the magnetic characterization. And each of the subsections I will conclude separately. In the second part, I will address the deposition of iron platinum particles inside borosilicon and silicon nanotubes. Then I show the magnetic characterization of the systems and finally conclude. And thirdly, I will address luminescent borosilicon filled with magnetic metals, and I will show the influence of the metal filling on the optical and magnetic properties. And finally, I will end up with a short conclusion. So these are typical borosilicon structures we are using. And as you see in these SEM top view images, with decreasing pore diameter, also the regularity of the pore arrangement decreases. And in the lower row, you see that also the dendritic growth of the pores increases with decreasing pore diameter. And especially for the magnetic applications, a quasi-regular pore arrangement is desirable. So in general, we use average pore diameters of 50 and 60 nanometers. So in the case of biomedical applications, we use borosilicon microparticles. So we remove the porous layer from the silicon substrate mechanically or chemically, and after subsequent milling we get microparticles of about 2 to 3 micrometer in size. For microborosilicon, for luminescent borosilicon, we use microborosilicon, which offers a branched morphology and structure sizes between 2 and 5 nanometers. And here we estimated the structure size from photoluminescence measurements, and we found a size of about 5 nanometers. A further approach is the use of silicon nanotubes. These structures are fabricated at TCU Fort Worth. First, zinc oxide seeds are deposited on a silicon wafer. Then the zinc oxide nanowires are grown. In a next step, silicon is deposited on these zinc oxide wires. And in a final step, the zinc oxide is etched away by a gaseous etchant. And as you can see in these TEM images at the right side, the wall thickness as well as the inner diameter can be tuned nicely. So first you see a very small wall thickness of about 10 nanometers and a diameter of about 80 nanometers. Here we have an inner diameter of 50 and a wall thickness of 40 nanometers. And in the last image, you see a very thick wall of 80 nanometers and the diameter of 50 nanometers. So now I come to the first section. For biomedical applications, it is well known that nanostructured silicon as well as iron oxide nanoparticles are applicable in biomedicine because both materials offer low toxicity. And so we combine these two materials, borosilicon and iron oxide, and silicon nanotubes and iron oxide. And loading of these nanostructures could be a promising candidate for biomedical applications, for example, magnetically guided drug delivery. So these are the iron 3 or 4 nanoparticles we are using. They are 10, 8, 5, and 4 nanometer in size, and they are fabricated in Madrid, Spain. And furthermore, we also used commercial particles of 10 nanometer in size. And here you see that these particles are quite monodisperse, whereas the commercial particles, they offer a quite big particle size distribution. So the fabrication of these particles has been carried out by high temperature decomposition in the presence of an organic precursor. And all particles are coated with an organic shell with oleic acid. This is to avoid agglomeration and also for stabilization. And the particle size is varied by changing the organic solvent. As the boiling temperature of the solvent is increased, the particle size increases. So since we want to use the system for bio applications, we looked at the cell viability, and we did this in using the Tribe Blue exclusion assay. Here in the left diagram, you see the cell viability for borosilicon filled with iron 3 or 4 particles of 4, 5, and 8 nanometer in size. And the cell viability is above 90%. And in the right diagram, you see 5 nanometer magnetite particles filled into silicon nanotubes. And in this case, the wall thickness of the tubes has been varied between 20, 30, and 40 nanometers. And also here, the cell viability is around 90%. So the cytocompatibility of iron 3 or 4 particles and also of borosilicon has been demonstrated in many studies by many different authors. And In the case of silicon nanotubes, the cell viability is above 90%, and also for the composite systems, borosilicon, iron 304, and silicon nanotubes and iron 304 particles, the cell viability is above 90%, which is quite promising. So the infiltration of the magnetite particles into borosilicon particles and silicon nanotubes is performed by applying a magnetic field. And here in these DEM images at the right side, you see the iron oxide particles inside the pores of the borosilicon and below inside a silicon nanotube. In case of the borosilicon, there are only a few particles, but this is because due to the fabrication of the membrane for DEM by focused ion beam, the iron oxide particles are sputtered away. And if you so if you look at this SEM image, you see that the iron oxide particles are filled into the pore, so they are completely filled. And here in the middle, you see 4 nanometer magnetite particles inside a silicon nanotube, 8 nanometer and 10 nanometer at the right side. So a further approach is not to use ready synthesized particles and infiltrate them, but to grow the iron oxide inside the borosilicon and silicon nanotubes. And therefore, we used two solutions. One solution, one aqueous solution, so the iron salt dissolved in water, and the second solution containing ethanol. And here we found that the iron oxide, in case of using the aqueous solution, is only deposited on the surface. There is no iron oxide inside the pores, but in case of the ethanoic solution, the iron oxide is deposited inside the pores. And if you look at this magnetic curve, you see that at room temperature, there is no magnetic remanence, which is a precondition for biomedical applications. These images here show the iron oxide inside the silicon nanotubes, also in using the ethanoic iron salt solution. So now I come to the magnetic characterization of these composites. And in the case of biomedical applications, the transition between superparamagnetic behavior and blocked state is of interest. So first, I say a few words about magnetic properties. So in general, if you look at a ferromagnetic material, it offers a domain structure. And by reducing the size below a critical diameter, the particles become single domain. And in this range, the coercivity reaches a maximum. So if you look at this curve, you see for bigger particles, they offer a multi-domain structure, and below a certain size, they become single domain. In this region here, they are stable, and by further reduction of the size, they become superparamagnetic. And this means that below a certain size, the remanent magnetization is no longer fixed in the direction dictated by the particle shape or the crystal anisotropy due to the thermal excitation. And so if a magnetic field is applied, it tends to align the magnetic moments, and the thermal energy tends to disalign them. So a hysteresis is observed and the superparamagnetism disappears when the particles are cooled to a particular temperature or when the particle size increases. So below the blocking temperature, the magnetization is stable. At the blocking temperature, this is the transition temperature between superparamagnetic behavior and blocked state. So, and to figure out this blocking temperature, we performed so-called zero field cooled measurements. So first the sample is brought to room temperature and then it is cooled down without a magnetic field. Then an external magnetic field is applied and the magnetization is measured up to 300 K and down to 4 K again. So here you see such zero field cooled measurements for 4, 5, 8, and 10 nanometer particles. And for 4 nanometer particles, we get a blocking temperature of about 12 K. For 5 nanometer particles, 15 K. And for the 8 and 10 nanometer particles, the blocking temperature is much higher. It's around 160 and 170 K. And the peak is very broad. And this is not only because of the bigger particle size, it's also due to dipolar coupling between the particles inside the pores. So this magnetic moment versus H to T curves also show the superparamagnetic behavior in this region. So you see there is a superposition of the curves between 200 and 100 K for 8 nanometer particles, and below there is a ferromagnetic behavior, and for 5 nanometer particles the curves coincide between 200 K and 20 K. So we also performed magnetic field-dependent measurements in 2 directions with an applied field parallel and perpendicular to the surface. And you see that there's a small magnetic anisotropy between these 2 magnetization directions, and this is due to magnetic coupling between the particles of adjacent pores. So now we look at the silicon nanotubes filled with iron 304 particles. We performed the same measurements, zero field cooled measurements. And for the 4 and 5 nanometer particles, we got the same blocking temperatures of 12 and 15 K. And for the 8 and 10 nanometer particles, we got a blocking temperature of 20 K and 40 K, which is much lower than in the case of the borosilicon. And this indicates that the particles do not magnetically interact. And we also investigated the commercial sample. And in this case, we found 3 blocking temperatures at 30 K, 110 and 160 K. And this indicates a very broad particle size distribution of these particles. So we also performed this magnetic moment versus H to T curves, and we also found that there is a superposition between 300K and 50K for the 8 nanometer particles, and here for 5 nanometer particles we have a superposition between 300K and 25K, which means that they behave in this region superparamagnetic. So these are the magnetic investigations of iron oxide chemically grown within borosilicon. And here we have a blocking temperature of 135 K, which indicates either there are very big particles or they are magnetically interacting, but nevertheless, we have no remnants at room temperature. and this is a precondition for biomedical applications. Here are the curves for iron oxide chemically grown inside silicon nanotubes. And here we have a blocking temperature of about 35 K. And also the hysteresis shows that there is no remanence at room temperature. So here in this slide, these results are summarized, and using these formula you can calculate the blocking temperature, whereas K1 is the anisotropy constant. And if you use the measured values of the blocking temperature, you get these anisotropy constants for the different particles. In general, the anisotropy constant increases with decreasing particle size and also with the occurrence of interparticle interactions. And this can also be seen in this table here. And for the commercial iron oxide particle sample, we calculated the particle size. So for the 30K blocking temperature, we have 10 nanometers. For 110K, 17.5, and for 160K, we have a particle size of about 20 nanometers. So you see there is a big particle size distribution. So we also did three-dimensional tomography by TEM, and a polynomial fitting process has been used to predict the local curvature of the position of the particles. And we found that the particles preferentially sit on a peak. And this here should be a movie showing the particles inside the pores, but unfortunately the movie is not working. So we also did some simulations. We did this with 5 nanometer particles inside borosilicon, and we compared them with our measurements, and we found that they are in good agreement. So this is the conclusion of the first section. Borosilicon and silicon nanotubes are filled with iron oxide nanoparticles of different size. The iron oxide has also been grown chemically inside the porous matrices. A variation of the particle size leads to tunable magnetic properties, especially the transition between superparamagnetic behavior and blocked state. A difference of the magnetic behavior between iron oxide filled borosilicon and silicon nanotubes has been observed. But for all investigated systems, the blocking temperature is far below room temperature, and the cell viability is around 90%, and thus the composite seems to be a promising candidate for biomedical applications. So now I come to the second sections, to hard-soft magnetic materials. So the combination of hard-soft magnetic materials can be used to control the magnetic switching behavior. And in this case, it's beneficial to have a regular arrangement of nanostructures and also to control the hard and the soft magnetic part. The aim is to deposit iron platinum as the hard phase and iron as the soft phase within quasi-regular arranged borosilicon or silicon nanotubes. And here I will show the deposition of the iron platinum. So far, the production of permanent nanomagnets has not been realized, but there is a big demand, for example, with respect to the applicability in data storage devices. One challenge is to produce nanostructures as small as possible, but big enough that the thermal energy does not dominate, so above the superparamagnetic limit. And the goal is to fabricate nanomagnets arranged in a three-dimensional array and to achieve an improvement of the energy products. So best to approximate the predicted one. So the energy product is determined by the coercivity of the hard magnetic phase and the saturation magnetization of the soft magnetic phase. Important is the volume ratio between the hard and the soft phase. And this is not so easily to control in the case of electrochemical deposition. So the soft phase should not exceed twice the thickness of the domain wall thickness of the hard phase. So now the growth of the iron platinum particles within silicon nanotubes has been performed in a multi-step process. So first, the silicon nanotubes are functionalized by EPTIS, then they are soaked in a solution containing a platinum salt and also an iron salt. And the iron salt the ratio of the iron salt has been varied. Then the samples are dried in a vacuum oven, followed by heat treatment, and then they are washed for several times with water and ethanol. Here you see silicon nanotubes filled with iron platinum particles, whereas the platinum to iron ratio is varied 1:1, 1:3, and 1:6. So here you see the particles inside the tubes for these different ratios. And we found that the average particle size is 5 nanometers. And what we also found is that the calculated platinum-ion ratios from the reactants is different than the ratios determined by EDX data. So here you see the particle size distributions for these different ratios, and in all 3 samples, the average size is 5 nanometers. Here you also see these particles inside the silicon nanotubes, showing the lattice spacing and the corresponding crystal structure. Here also these particles inside the silicon nanotubes, and in the row below you see an EDX mapping showing the silicon, platinum, and iron content. And here at the right side in the small image, you see such a sample silicon nanotubes filled with iron platinum in a test tube, and it can be moved easily by a magnet. So we also filled the iron platinum into porous silicon, and the formation is nearly the same as in the case of the silicon nanotubes. The only thing is that the porous silicon did not receive the EPTIS functionalization. And here you see these porous silicon structures with the iron platinum particles inside. And here this SEM image shows a few individual particles inside a pore, and in this case the average size is 10 nanometers. This can also be seen here from this particle size distribution. We have a broader particle size distribution than in the case of the silicon nanotubes, and the average size is 10 nanometers. So for comparison, we also filled cobalt particles into silicon nanotubes and borosilicon, which can be seen here in the left. And at the right side, the presence of the cobalt particles inside borosilicon has been evidenced by EDX spectroscopy. So now I come to the magnetic characterization of these systems. So the silicon nanotubes filled with iron platinum particles with different iron content have been investigated with the ratios 1:1, 1:3, and 1:6. And the magnetic field dependent measurements show that the coercivities of these different samples vary in the range of 5%. And for the borosilicon filled with iron platinum, whereas the ratio is the same, 1:1, 1:3, and 1:6, we also found that the coercivities vary in the range of 5%. So in these tables, these results are summarized. And you see that the coercivities for iron platinum within borosilicon varies between 560 and 530 Ørsted. And in the case of silicon nanotubes, the coercivities vary between 228 and 240 Ørsted. See, the variation is similar, about 5%, but in the case of the borosilicon, the coercivity is much higher. They're about twice as high than for the silicon nanotubes, and this is due to the bigger particle size. Here, this diagram shows the coercivity independence on the temperature, and you see the coercivity decreases with increasing temperature, which shows a ferromagnetic behavior of the samples. Here you see a comparison of cobalt particles filled into silicon nanotubes and iron platinum particles filled into silicon nanotubes. This is the red curve, and you see that the coercivity for the iron platinum sample is much higher. It is twice as high than for the cobalt sample. And here the same measurements have been done for borosilicon filled with cobalt and iron platinum, and also in this case the coercivities for the iron platinum sample is much higher than for the cobalt sample. And if you compare iron platinum within silicon nanotubes and iron platinum within borosilicon, you see that for the borosilicon sample, the coercivity is about twice as high than for the silicon nanotube sample. And this is due to the bigger particle size. So here, this all is summarized again in this table. Coercivities for iron platinum within borosilicon and cobalt within borosilicon is always higher than the particles grown inside silicon nanotubes. So in conclusion, one can say that nanostructured silicon has been filled with iron-platinum nanoparticles. The iron-platinum ratio has been varied for both types of samples, and the different iron content leads to a variation of the coercivities of about 5%. Iron-platinum grown inside silicon nanotubes offers a coercivity twice as high as of cobalt particles inside silicon nanotubes, and there are similar results for the borosilicon samples. And borosilicon filled with iron platinum nanoparticles offers coercivity twice as high than silicon nanotubes filled with iron platinum particles. And this system gives rise for magnetic applications in magnetic sensor technology or also in magnetic data storage. So now I come to the last section, which addresses luminescent borosilicon. So microborosilicon shows light-emitting properties in the visible. If you fill borosilicon with a ferromagnetic metal, it shows specific magnetic properties. And we want to exploit the localized surface plasmon resonance of the deposited metal structures. And the aim is an appropriate coupling of the emitter field of the silicon nanostructures with surface plasmons of the metal to increase the luminescence intensity. So on the one hand, the system is of interest to combine optics and magnetism in one material with adjustable optical properties by an applied magnetic field. On the other hand, the magnetic properties are adjustable by the deposition conditions. The system offers a specific magnetic response due to the nanicized deposits and the branched morphology. So the composite is also of interest in terms of electrical transport, especially the influence of the metal filling on the percolation limit. And why we use nickel for the deposition is because nickel has a plasmon resonance around 450 nanometers, and it is a significant optical feature of nickel. If you compare gold spheres of equal size, the nickel resonance is weaker because of the large imaginary part. And if you place an emitter, for example, a quantum dot in the direct vicinity of metal structures, a strong coupling of the plasmonic modes with the quantum dots is observed. So in our case, the metal plays two roles. First, the coupling of the surface plasmons of the metal to the electronic excitation of the nanostructured silicon. And secondly, it acts as magnetically active material to enable the influence of a magnetic field on the optical properties. So the silicon emitter coupled to the plasmons of the nickel particles, and this leads to an enhancement of the photoluminescence. And the spacer between the emitter and the metal in our case is silicon oxide. So the microborosilicon is filled with nickel by electrodeposition, and the presence of the nickel inside the pores has been evidenced by EDX spectroscopy. We also filled cobalt into microborosilicon by electrodeposition, and in this case we performed EDX spectroscopy at two positions, in the middle of the porous layer and at the bottom of the porous layer, and we found that the cobalt content decreases with increasing pore depths. So it decreases towards the pore bottom. For comparison, we also filled small nickel particles into mesoporous silicon, which offers oriented and separated pores. And the particle size in this case is comparable to the particle size in the case of microporous silicon. It's a few nanometers in size. So now I come to the optical properties of the microporous silicon. And here you, at the left side, you see the photoluminescence for metal-filled borosilicon, and you see that the photoluminescence peak for initial borosilicon, it's around 620 nanometers. It's the bright blue curve, and it's this blue shifted with increasing metal filling. And we also observed a decrease of the photoluminescence lifetime with increasing metal filling. So here the left diagram shows the dependence of the photoluminescence peak on the deposition time. You see it decreases with increasing deposition time, and the photoluminescence intensity increases with increasing deposition time. And the faster decay times of nickel-filled borosilicon compared to bare borosilicon can be interpreted, by a decrease in the radiative lifetime with increasing metal filling. So with increasing nickel filling, we have a higher amount of interconnected nickel deposits, and we get an increase of the photoluminescence intensity and a decrease of the photoluminescence lifetime, and this can be interpreted by a decrease in the radiative lifetime. The enhancement of the photoluminescence intensity with increasing metal filling is interpreted by the coupling of the silicon emitter to the nickel plasmons. In the case of the cobalt filling, we did not observe a photoluminescence enhancement so far, and we think this is due to a wrong spacing between emitter and metal. We think that the oxide layer is too thick. So now I come to the magnetic characterization of these systems. First, a few words about magnetic anisotropy. In the case of bulk material, the magnetic anisotropy is mainly dominated by the magnetocrystalline anisotropy. And in the case of nanostructured materials, the magnetic properties are characterized by their geometries, and the magnetic anisotropy is often dominated by the shape anisotropy. And this can be seen here in this sketch, that the easy axis is along the wire direction and the hard direction is perpendicular to the wire. So the magnetostatic energy of the spin configuration for the easy axis is always lower than for the hard axis. And in the case of films, with the reduction of the film thickness, the spins rotate in such a way to minimize the magnetostatic energy, and the spins rotate in the plane of the surface and they form so-called nail balls. And by further reduction of the film thickness, out of plane magnetization is observed, which is known as perpendicular media. Here you see magnetic field-dependent measurements performed in two directions with an applied field perpendicular and parallel to the surface. And you see that the magnetic anisotropy between these two magnetization directions is quite big. And what you also see is that the easy axis is for an applied field parallel to the surface. And if you look at the left diagram, you see the coercivity independence on the deposition time, and you see that the coercivity increases with increasing deposition time. And also the magnetic remanence increases with increasing deposition time, which is shown in the right diagram. So we also filled borosilicon into we also filled cobalt into borosilicon, and we did the same measurements with an applied field perpendicular and parallel to the surface. And also in this case, the EC axis is for an applied field parallel to the surface, and we have a big anisotropy between these two magnetization directions. And if you compare borosilicon filled with nickel and borosilicon filled with cobalt, you see that the anisotropy is even more pronounced in the case of cobalt filling. So in the case of microporous silicon, we can say that the coercivity as well as the magnetic anisotropy depend on the filling time due to more or less interconnections of the metal deposits. The coercivity decreases with less interconnections, and it approximates to a superparamagnetic behavior. In the case of nickel filling, the coercivity decreases from 450 Oersteds for filling time of 15 minutes to a coercivity of 150 Oersteds for a filling time of 5 minutes. And in the case of cobalt, the magnetic anisotropy between easy and hard axis magnetization is even more pronounced than for nickel-filled samples. So in the case of mesoporous silicon, the samples offer oriented and separated pores. We also filled nickel particles of a few nanometers in size. And due to the size, the particles would be superparamagnetic, but due to weak magnetic coupling, they show a ferromagnetic behavior. So we performed the same magnetization measurements with an applied field perpendicular and parallel to the surface. We found that there is a small magnetic anisotropy between these two magnetization directions, but what we also found is that the EC axis is for an applied field perpendicular to the surface. And this is due to shape anisotropy. And the due to weak magnetic coupling, we have this small anisotropy between the two magnetization directions. So in the case of mesoporous silicon, we can say that the coercivity and also the magnetic anisotropy strongly depend on the shape and the size of the metal deposits, as well as on the magnetic interactions between the deposits of adjacent pores. The coercivity decreases with increasing lengths, so the coercivity is higher for particles than for wires. The magnetic anisotropy between easy axis and hard axis magnetization increases with increasing distance between the pores due to less magnetic interactions. And in the case of nano-sized nickel particles, small magnetic anisotropy between easy axis and hard axis is observed due to weak magnetic coupling. So in conclusion, we can say that microborosilicon offers luminescence in the visible. The photoluminescence peak can be shifted by the metal filling. The photoluminescence intensity is enhanced with increasing nickel filling. In the case of cobalt filling, we did not observe such an photoluminescence enhancement. Maybe this is due to the wrong spacing between emitter and metal. The magnetic response is influenced by the amount of the metal filling. So the coercivity decreases with less interconnected metal structures, and the magnetic anisotropy increases with increasing deposition time. And what we observed is that the easy axis is parallel to the surface, which is a film-like behavior. And for mesoporous silicon filled with nickel particles, we observed a small magnetic anisotropy, and the easy axis in this case is perpendicular to the surface. So altogether, we can conclude we work on 3 routes to employ a composite system consisting of nanostructured silicon and magnetic structures. First, we fill iron oxide nanoparticles into nanostructured silicon, and we showed that the cell viability is above 90%. Furthermore, all these systems show a superparamagnetic behavior at room temperature, which is a precondition for biomedical applications. In the case of hard soft magnetic materials, we demonstrated the deposition of iron platinum particles within nanostructured silicon and the influence on the energy product. And for nickel-filled luminescent borosilicon, we showed the influence of the metal filling on the optical and magnetic properties. And the magnetic response shows that the system offers a magnetic easy axis for an applied field parallel to the surface, which is in contrary to mesoporous silicon. So these are the people who are working on this topic and our collaboration partners. And thank you for your attention.
Thank you very much, Petra. Yeah, very nice talk on different topics. And actually, maybe the people here are wondering about the bio applications of these materials. Actually, the last part that you presented on the photoluminescence, it reminded me something about Raman spectroscopy, like SERS. One uses the plasmon frequency also, or one excites at that frequency, and then one gets an amplification of the Raman signal, for example, for some bio detection. And here it will be very interesting if it works with photoluminescence too. Um, Actually, yeah, it was very interesting for me that the intensity increased, but the lifetime of this luminescence decreases. Um, many times in semiconductors, the people are not adding metals sometimes because they think they will get some recombination of, of the of the carriers, no? But in this case, I don't know if it is because of that the lifetime of the luminescence is smaller or lower. Yeah, the lifetime is smaller. What do you think? Do you think it's because of the states that are inside the gap of silicon that are introduced by the metal, Petra?
Maybe, but we are not completely sure about this. We are still working. We are at the starting point in the case of the luminescence borosilicon. So since we now got all labs renovated and get the new instrument, so we had not so much time to work on this topic, but what you said, I think this could be a reason, yes. But we are also not completely clear why we did not observe an enhancement of the luminescence in case of the cobalt. We think it's due to wrong spacing, but we are not completely clear about that. Because it's in case of microborosilicon, you need DEM images to see something clearly, and so it's long work.
Yeah, actually, it's an interesting work. What I told you also is, yeah, about this introduction of some states in the gap. Um, that is one thing, no? But on the other hand, it is very interesting that you are observing this increased luminescence. But it is also interesting that you are exciting. I don't know if it is true. If you are exciting also with light in the wavelength of 425 or something like that nanometers, is it true?
Yes, yes, it's true.
Because usually, yeah, in some experiments with porous silicon, one is usually exciting maybe um, with UV light, no, is in 250, 300, but not above 400 nanometers. Maybe by using other kinds of particles, maybe smaller ones, one can shift or tune the position of the plasmon resonance and to be more according to the highest excitation of the luminescence of porous silicon. I don't know, but you told me that you are
Yes.
starting with that topic, no? Um,
Yes, we are at the starting point, but
mhm,
this is an interesting aspect.
mhm.
But yeah,
Yeah, very very interesting. On the other hand, yeah, I don't know if the people from the from YouTube who have any questions. If while we wait for some questions there, here I have a different question. In the first part, when you were showing some magnetic measurements, you were saying that having a remanence close to zero is important for some bio applications. I don't know if you could mention a little bit about that. Why is important that the remanence is close to zero?
well, if you have a remanence, the particle is ferromagnetic, and ferromagnetic means well, it's not desirable for bio applications. If you switch off the magnetic field, you want that the particle is not magnetic anymore. And if you switch on the magnetic field, for example, for magnetic field guided drug delivery, you move the particle and then it should lose the, if you switch off the field, it should lose the magnetization. And maybe if you switch it on again, you can remove the particles. But the ferromagnetic behavior in general would not uh, be preferred. So
So it's not so controllable, no? It's not that you have magnetization just when you want, but it's always there, and that is not desirable for some
yes, so
application.
you want it super paramagnetic, so you have two states, up and down. So if you apply magnetic field, it's switched on, and if you put it away, it's switched off. So it that's preferable.
Yeah, thank you. And on the other hand, it's about when you were depositing some metal inside nanotubes and porous silicon, you were mentioning a difference in coercivity that was given by the particle size. Um, was this particle size influenced by the diameter of these tubes or bores, Petra? Or
No, no, it's
what
from
is?
the growing process. Um, it's not so easily to control the growth inside the tubes and the borosilicon. And in the case of the silicon nanotubes, we could get 5 nanometer particles, but in the case of the borosilicon, the particles about 10 nanometers. And so the magnetic properties are different. So they have a higher coercivity due to their bigger size. So the
That's why.
final aim is to have iron platinum
Mhm.
and also iron as the soft phase, but the soft phase to control it, that it's a very small particle, it's very hard to do. So if you do films by epitaxy, it's quite easily to control the thickness, but in the case of chemical growth, it's hard to control. So
Yes, it's difficult. I
that's
know. um, and have you observed any any influence of silicon or on your magnetic characterization or magnetic properties of your materials?
the silicon is diamagnetic, so you just have to subject the diamagnetism of the sample.
Okay. My
So
question is, for example, if you have a lot of porous silicon and maybe just two, three particles, magnetic particles, is it the same if you have very less porous silicon and also that those two, three magnetic particles? The amount of silicon makes a difference?
you mean the porosity?
The
Um,
porosity or the yeah, how much you have? Yeah, actually, how much bulk silicon is in your
um,
composite?
the bulk silicon, it's only the diamagnetic contribution, but in the case of the porosity,
Mhm.
um, if you have a very thin pore wall, uh, a distance between the pores, uh, and you have a lot of particles, they can interact between the pores. So you have different magnetic interactions, not only inside the pores, but also between adjacent pores. So, but the bulk silicon, it's only the diamagnetic contribution.
Okay, okay. So you just have to subtract it, but it is not so um, making a big difference between measurements if you have less or more silicon in your composites. Yeah, no?
Um,
For example, if it makes a difference, I guess I'm not so pretty sure that your silicon nanotubes are a little bit porous, have porous walls.
yes, yes.
Yeah. And in the case of porous silicon, the walls are not necessarily porous.
No,
Mhm.
the but for the magnetic characterization, it's only in the case of the silicon nanotubes, for example, if you have particles inside the pore wall, you have more interactions, but the amount of the silicon is not so important for the magnetic characterization. It's more uh, the localization of the particles, if they are close together or not so close.
Okay, okay. Then that's why to have these mesopores or micropores with some branching, and so it is beneficial for your purposes, no? If it,
In the micropores, they have this sponge-like structure, and so also the metal you fill into these structures have these branches, and this is because we get this film-like behavior with the easy axis with an applied field parallel to the surface. But in the case of the mesopores, where you have straight pores, you have the easy axis for an applied field parallel to the pores, perpendicular to the surface. And this is due to the shape anisotropy, because in general, the particles interact within the pore and there is less interaction between adjacent pores.
Yeah, very good. And I don't know, you told me that nowadays you are more on the magnetic properties of these materials and that you were using before also for some bio applications. I don't know if you could comment a little bit about that, about those applications that one where one can use these uh, particles of porous silicon with some magnetic stuff. I think you mentioned a little bit about drug delivery.
Yes, this was our aim to use it for, well, our aim it to show that it could be work for drug delivery. So you load the borosilicon or silicon nanotubes with these particles, then functionalize with some material. For example, I don't know, if you want to bring it to a tumor, you can inject it, move it by a magnet to the tumor, because otherwise, if it's only going in the bloodstream, a lot of the particles go to the kidney and liver, so it's not many of them reach the tumor where they should go. And then the borosilicon uh, resolves in body fluid, so depending on the porosity, and it gives the material to the tumor, and the particles can be removed by a magnet again. So that's the rough idea about that.
So that it is important that they were magnetic so that you can introduce them and move them to the places
Yes,
you want to
yes,
move them, no?
yes.
Okay. Yeah,
Other
it's
people use only magnetic particles for uh, tumor therapy by hyperthermia. So it's also a big application for these particles.
yeah, very interesting. So, Petra, I think with this we can finish. So, thank you very much. It is this very interesting. Also, these micrographs that you were showing with these particles inside, and yeah, one can imagine many things that one can do with those particles. For example, with this for these bio applications, but for also for some other stories, no? But for example, the last story of the luminescence, I can imagine it also for some bio stuff. So one can do many things with this porous silicon or silicon micros or nanostructures. There is a lot that one can do there. Yeah, we have been working on this for several years now in porous stuff and porous silicon, and one can still find many possibilities. Or what do you think?
Oh, yes, sure. Yeah.
So thank you very much, Petra. It was a pleasure to have you here in Mexico. But
Yes, thank
now,
you very much for the invitation. It was a pleasure for me.
virtually, but hopefully we can meet us again here or there in Europe. But yeah, here in Mexico, we organize many conferences here in Cancun or so, material science. So we can meet again somewhere in
Yeah,
the near
hopefully
future.
it would be good.
Yeah, and so give my regards to Clemens and
Yeah, thank you very much.
Thank you, Petra, for being here and for your interesting talk. Thank you very much.
Yeah, thank you for inviting me and hopefully see you again.
yeah, see you in the future.
Yes.
Ciao, ciao.
Bye.
Bye. Bye.